Good day, everyone. My name is Zhidong Zhang from ETH Zurich. I'm glad to take this opportunity to present our recent work on modeling effect of coarse aggregate on oxygen transport and corrosion product precipitation in reinforced concrete. This study received financial support from Swiss National Science Foundation and the European Research Council. Here is a brief out of this presentation. First, I will talk a bit about the research background, then models that I used for simulations. Last, I will show some result about effect of coarse aggregates. We all agree that corrosion-induced damage is one of the main causes for the failure of reinforced concrete. In conventional modeling method, they assume corrosion product uniformly grows from rebar, so that create a layer around the rebar which can accommodate corrosion product. The created stresses similar to thermal expansion and hydraulic pressure. However, in this SEM image, we can see corrosion product can penetrate into concrete matrix. The distribution corrosion product is highly affected by microstructure of concrete. Consequently, the induced stresses are not uniform around the rebar. To consider the heterogeneous microstructure, our previous study have proposed a method to describe the microstructure of concrete. So we call it image-based homogenization method. From SEM-BSE image, we calculate the porosity and the permeability distribution. Therefore, we can use them to simulate mass transport in concrete. The advantage of this method are obvious. There's no assumptions on homogeneous motor matrix, aggregate size, and the thickness of our design. For those who are interested in this method, please read this paper and follow our recent publications. The created domain was further used to simulate corrosion product transport and precipitation. Here, I provide two examples of simulation result. So we have steel bar on the left-hand side. So it's release Fe2 plus ions. So we compare two cases. One is an accelerated corrosion condition with high Fe2 plus release, and the other one is a natural corrosion condition with low Fe2 plus release. So those animation shows the porosity reduction due to corrosion product precipitation. So we clearly see the difference between those two cases. We also see that the present of aggregates can change the distribution of corrosion products, such as around this aggregate, we have more corrosion product, but in some region, we have less corrosion product because more aggregate present there. Therefore, we further investigate the effect of coarse aggregate on corrosion product transport and precipitation, which is the topic of this presentation. First, let me briefly recall the model we used. For corrosion product formation and precipitation, we use the connected models. In this model, there are 5 processes, including Fe2 plus released from steel surface, Fe2 plus ion diffused to concrete matrix. Meanwhile, we have the precipitation of R2 hydroxide. Fe2 plus ion also oxidized to Fe3 plus and precipitated as iron 3 hydroxide. In this model, we assume anodic and cathodic reactions happen on the same location. So that's why we have this equation for the corrosion reaction. For Fe2 plus oxidation, so we assume this kind of connected reactions is depend on the concentration of Fe2 plus and oxygen. When the concentration of Fe2 plus above a certain threshold, so it can precipitate as iron 2 hydroxide. It also follows this kinetic reaction. For iron transport, we use Nernst-Planck-Poisson equation to calculate. The electromigration is considered in this model. The Poisson equation is used to calculate the potential created by different speed or charged ions. Here, we only consider the saturated condition, so there's no water flow. For the tutorosity, so it calculated based on measured porosity. As shown by this figure, we found a good correlation between tutorosity and the porosity. Last, so the porosity reduction is considered because the precipitation of iron 2 plus hydroxide and iron 3 plus hydroxide. So in this presentation, so the investigated factors are listed here, including aggregate domain ratio. That means that is an aggregate fraction in concrete. And aggregate shift, we studied two aggregate circles and ovals. And the RTZ effect and the distance between steel and aggregate. Here, I just show one example of circle aggregate with three different aggregate domain ratio, 0.45, 0.3, and 0.15. So three aggregate size, 2, 1.5, and 1 millimeter are considered according to the full aggregate gradation. About the RTZ, so we create a thin layer around the aggregate. It's about 100 microns thick, which agree with the measured value from the literature. If we just take one part and zoom in, we can see the porosity decrease from the surface of aggregate to the bulk of cement paste. So in the last, the porosity about 0.1 is the measured porosity from the bulk paste. First, let's see effect of aggregate fraction on corrosion product transportation and the precipitation. So we compare three cases here. So the animation shows the oxygen level of three cases. We can see for the high aggregate domain ratios, the oxygen depletion happened earlier. But for the lower one, so oxygen depletion happened later. So they have the different times as shown here. So of course, for the oxygen depletion, it's only happened on the surface of steel because this part the oxygen consumed faster. Yeah. So then let's see the effect of aggregate shape. So this animation shows result of oval aggregate, the oxygen depletion versus the aggregate domain ratio. So we have those two figures. This one shows the circle aggregate, this one shows the oval aggregate. Clearly we see for oval aggregate, so the oxygen depletion time is much shorter than the circle aggregate. This because when we create the domain, aggregate randomly distributes in the simulation domain. Because the high aspect ratio of ovals, they can increase the length of path that oxygen needs to diffuse. In other words, for the oval aggregate domain, so the tutorosity effect is higher. However, with the increase of aggregate domain ratio, the difference between circle and oval shapes gets smaller. So at this level, they are very similar. Those figure also clearly shows the effect of RTZ. So we have this dashed line result from the RTZ and the bottom line from the domain without RTZ. So it's clear RTZ works as a path stand for oxygen diffusion. So about the effect of distance between steel and aggregate. So we can see we have aggregate on the surface. So if we just zoom in the closed one, we investigate the distance from the steel surface and the surface of aggregate. From the figure, it clearly shows that with the increase of this distance, the time for oxygen depletion increases as well, because of the barrier that aggregate work as is away from the steel, and more oxygen can diffuse in to support a corrosion reaction. Another observation in this simulation is the precipitation of R2 hydroxide, as those animation compared here. So we can see for the shorter distance, we have more R2 hydroxide precipitation, but for the wider one, we have less. This because when there's no enough oxygen, R2 ions can diffuse away from steel surface and precipitate close to the aggregate. In our experiment, we observed a similar phenomena. So this picture shows corrosion product in carbonated mortar. So we have aggregate, we have steel, and this is the boundary. So from this part up, we can see the layer of corrosion product from this line down. So we don't see the corrosion product. So if there's no enough oxygen at the steel surface, so these parts tend to be the anode in corrosion reaction. So that's why we see more corrosion product. Conclusion, this study, we demonstrate that the present of aggregate can slow down oxygen diffusion. The higher aggregate domain shows the more significant effect. We also see all aggregate have stronger tutorial effect than the circle aggregate. So the present of RTZ provides additional channel for oxygen diffusion. So it's quite clear shown in this study. More corrosion product precipitation in narrow region between steel and aggregate. So the narrower this region, the faster oxygen depletion. So that's why we see more R2 hydroxide in this region. This is the end of my presentation. So if you have any question, please ask me directly or send email to my email address. Thank you very much.